This is about where we left off last time. And I'll just make sure we hit this point again because it's super important. If you look at this code, what's happening? A012, it's a list, but is it really a list? No. A is a reference to a list. So when I say B equals A, what gets copied over? The reference, not a list. So if I print out AB, I see this. But what's the catch? How many lists are there right now? 1. How many references to that list are there? 2. So that's why when I say B at index 1 become 99, it changes it for both lists. But again, there's really only one list, 2 references. So that's why it appears to change in both. But in reality, there really is only just one list. So that's the big thing. If you expected this to work like, oh, this would have been an independent list, no. You would have to explicitly copy the list. And where did I show you last time the easy ways to copy? Like this, right? You could say some list.copy, or you can slice the whole list like that really quickly, and just this returns a whole list of the full list. So that'll also make a copy. And here, do this activity real quick. I'll give you a few minutes for this one just to convince yourself that, or just to like really familiarize yourself what the difference is, how you explicitly copy, and how it should react in both cases. Here's how I convinced myself. I evaded, okay, L, ABC, whatever. And by the way, why am I always doing ABC? Because if I do 0, 1, 2, it can get confusing by what's the index and what's the value, because they'll be the same. So that's why I use ABC. So ABC, L copy is L.copy. I also could have done this with that slicing thing like this. That also would work. And then L alias, I just copy over the reference. I print the 3 out. We see ABC, ABC, ABC. 3 lists, seemingly. But at this stage, Like, how many lists are there? No. 2. This makes a new list, the copy, right? So if I change L at index 1 to whatever, if I print out L, I see the change. If I print out L copy, there's no change because we copied it before we made the change. And then the alias gets changed as well. What's up?
I've copied your code here, right? I'm trying to run it. It says that there's issues in my codes with the words copy and alias.
Well, I don't know. Did you use underscore?
Yeah.
No, then something's wrong.
Wait. Hey, Andrew.
Yup.
Did you use a 1 or an L?
I used an I.
Oh.
Well,
Oh, no idea.
there we go. Other questions? Okay, so where this can get, I mean, this can become a problem in a variety of different places. And if you remember last time, yesterday, I was talking about how if we pretend things are immutable, this problem somewhat disappears. Take strings, for example. Strings are objects, so I could have a bajillion different references to a single string. And because I have no way of modifying that string, like the actual string, I don't have an opportunity to like mix something up like that, right? Now lists are mutable, but if we pretend they're not, we kind of eliminate that problem, and that's what happens in assignment 2. But back to this. So whenever you have a function, like here's one, add to list. It takes some list and some arbitrary value, okay? If I say SUMList.append value, this parameter, like if I call it here, this parameter will make a copy of what's in here, which is a reference. Meaning this will be an alias. All right? So why is this important? Well, because this is an alias to this list. When I append to it, I'm going to modify the thing that a list references. Do you see what I mean? So all this alias stuff happens with parameters as well. Now this is a function that I would say has a side effect. Okay? It is an impure function that has a side effect. And what do I mean by side effect? Well, functions typically receive some input and produce some output. I don't know, whatever, right? You give function, you can think of a function as a box, right? You give it input, it produces output via return. And this is like the args. Right? Right? So our parameters are the input, return is what we get. This function, though, has a side effect, meaning it somehow goes and modifies a list somewhere else. You see? How? Well, SUMList is a reference to this list. This list doesn't exist inside this function. It exists elsewhere. And then we modify that list via the reference. And so it made a change. So that is a side effect. And in fact, there's nothing returned here. All right? Now, you can kind of cheese this particular situation to fix it. But to be clear, having impure functions is not intrinsically bad or evil. It's fine, but some people really like to make sure they have pure functions. All their functions, like none of their functions have side effects. But any questions about this? Because understanding this is going to be important. I'm going to copy it and run it. Right? So let's think about what happens here line by line. I've got that function. Let's say I have a list is a reference to this list. And what is it? A, B, C. A, B, C. Right? Okay, great. The next line goes up to that function, add to list. Oh, okay. So now we kind of like jump over here. All right? I'm in that function, and I'm running the code in the function. And I have a list, or what do I have it called? Some list, which is a reference to this function, this list that exists outside. And it also has like the value. And then inside of it, all it says is, okay, go here and append 99. Don't return anything. This function's done. We come here, we print out a list, and obviously we see that. That's how it's working. All right? It's impure. It has a side effect. Do you get the idea of a side effect? This function didn't return anything. The return is nice, but when this code goes, when this function goes and modifies something somewhere else, that's a side effect. Okay? Cool. And there is value in pure functions. There are some programming languages where you can't have side effects without really forcing it. But that's a whole other thing. Any questions about this before I move on? So there are a few ways. All right, side effect. Okay, perfect. Okay, cool. So add to list is an example of function that has a side effect. Function modifies the list that was passed by reference. This is a side effect from a mathematical expectation of a function. A function maps some input to an output, right? So if I give you the function x, y, z equals x plus y minus z and ask you to evaluate, you can just do it, right? You don't expect the values of x, y, and z to change, right? That's a pure function, all right? But imagine if somehow magically after evaluating this, the value of x changed to like 77. That doesn't make any sense. That makes no sense at all. That would have been a side effect. So we can rewrite, like, look, anything you do with a pure function, you can do with an impure function and vice versa. You just have to make sure you're addressing it. Again, there's nothing wrong with side effects and impure functions, but they tend to sneak up on you. The problems that they create will sneak up on you. So after a little while of programming, you realize you've kind of like backed yourself into a corner. You can still deal with it, but it might get more complicated. So here is a different version of that function where it first makes a copy of some list, it modifies the copy, and then it returns the new list. So now a list is left unchanged. And it returns a new list that is a different version. Like it's based on whatever some list was, but it's like the updated one. Do you see what I mean? Cool. Yeah. There are like a lot of theoretical benefits to this, like both mathematical and like software engineering-y design. It's a little outside the scope of this course, whatever, but long story short, it's kind of nice to like pure functions, but at the end of the day, sometimes it's just really easy to just deal with side effects if you're just solving a problem. Yeah.
Let's go back up to the example.
Yeah.
Okay. Okay, so you made a list, and then you put it in the function, and then you changed some list. So then the list in the function is a new function that's not a list, right?
The list in the function, so let's slow it down. A list is a reference to a list. I call the function add to list pure. It takes a reference and the value I want to add. So once we jump up here, some list is a reference to this list. Okay? Then we immediately make a copy of it and assign it and put the reference to that copy into new list. I append the value to new list and then I return new list. So now they are treated entirely independent.
Okay, gotcha.
That's the idea. So this is a way to make it pure. Another way you could have, like, look, you could kind of cheese this a bit by being like, look, I don't actually care if the original one gets modified. So this is kind of a way to like, this is kind of a way to like obfuscate your side effect. It still has a side effect, but it ultimately didn't matter. Because what happens is, it gets a reference to that one list, we modify it, we return a reference, which was entirely unnecessary, and then we overwrite what was in the original one, which is still a reference to itself. So it kind of hides the side effect. It still has a side effect, but it ultimately kind of like makes it meaningless because now there would have been no way to get back to the, like it would necessarily have to change. Don't worry, it doesn't matter. This is fine, but this is a cleaner, more pure version of that. So any questions about this? To know if your code has a side effect, it really is just answering the question, does my code modify any value outside of itself? Do I modify like something that was passed to me? This is only going to happen when you have a reference, all right? And if you don't have a return, but your functions are changing things somewhere in your code, you definitely have side effects. It's not necessarily bad, all right? It's not intrinsically evil or anything. The word impure doesn't mean it's evil or bad, but pure versus impure, okay? When in doubt, maybe go for the pure function. Sometimes making an impure function is going to get the job done like that, and it's good enough. You know, use your judgment. So yeah, what's nice about this? Yeah, the one that was passed by reference, yeah, sure, we get a copy of the reference, but then we go out of our way not to modify the original list. We make a new list, and then modify the new list, and then return it. Cool. Okay? Now some facts about lists, things you can do with them. All right, so here's the list, some list, 10, 11, 12. I can print out the length of the list. I can get the length of a list by using len. All right? Like empty strings, you can have empty lists. You can have a list that exists, but there's nothing in it. Right? So in this case, like, here's me creating an empty list. Remember how we did it with strings? You have an open quote, close quote. Here's how you do it. You do it with the brackets, the square brackets. Print it out. We see that. What's its type? It's a list. What's its length? It's 0. So that's what that would say. You can have lists inside of lists, though really you could have lists with references to other lists inside of it. That's really what's going on there. But there we go. And to index, like pay attention to how we index it, okay? Like some nested list at index 1 will be this whole list. So if that's a whole list and then I index this, which is a list 0, I get the, oh no, that would have been this whole list, pardon me. That would have been 0, this is 1. If I get 0, it would be this list's index 0. Okay? Okay. You can append to lists. This is a mutating function. It modifies the list. You can concatenate lists with plus, which is pretty neat, pretty simple. You can repeat a list with multiplying it, just like you can with a string. And here, let's, real quick too. Like if you wanted, if I had like A equals A, B, C, I can like A dot append Z, print A, right? Like that'll work. But I could also do, and this is interesting, pay attention. I can do A plus Z, right? Because that'll concatenate the lists. But when you do that, that actually returns a new list. So if I say B equals that, print A, print B. Oh, that's a string. There. So this is a neat way to append without actually causing like a side effect, right? So append actually will go and modify A, but the concatenation of A with the with a list with one element in it that I want to append, that concatenation is a new list. You see? Kind of neat. When do you use what? Whatever. It depends on what you want to do. What's up?
Can you append at a specific index?
So, let's see. First, A dot insert might be what we want. Right? So, index 1, Z print A. So there you go. There's a lot of like, clear, copy, count, extend, index, insert, pop, remove, reverse, sort. So yeah, there's a couple of things stuff built in there. And I'll give you a few minutes to do this activity. I think it's important. And all of it. Right? So do this part. And then do this part. Okay? Because it'll actually open up a good question that we need to really think about. If you're drawing a blank on where to start, there's a good place to start.
I just have a question.
What's up?
So I've heard of like for I in range, but like how would I tell it to get like for each thing list if that's possible?
Well, you would need like a parameter for that function, right? Because new list only doesn't exist inside that function. But that's the general syntax for iterating over a list, the contents of a list.
How does it know like
Were you,
the like how does it know what num is?
well, that's how that for loop, for each thing in a collection of things. So the first time through the loop, it would be the first thing, then the next thing, then the next thing, then the next thing. I see a lot of people working way too hard. From the syntax I was seeing, you're digging yourself into a hole most of the time, it seems. Here's mine, right? Yeah, you could do it with a while loop, but with a for loop, simple enough, right? My sum, it takes a list, returns an integer, great. Running total, it's going to keep track of the running total of the elements. And then for n in some list, just add n to the running total. Once you're done, return running total, right? Any questions about that? Cool. So, and I can test it here, 249. Great. Now you might be thinking to yourself, well, why would there's two parts to this. Why would I write my own when they have a built-in one? Okay, fine, fair enough. Yeah, great, cool. But like, why even like write all this code when Python knows how to sum? You have to be careful. Just like print, if you go and you open up the print function, there's a bunch of code in there. Okay? You didn't write it. You didn't need to write it. Python didn't just know how to print. Someone had to write the code to tell Python how to print. Python doesn't just know how to sum. Go sum it. Oh, no. It's a function. And if you were to go look at that function, it's going to look a hell of a lot like this. Okay? How else are you going to sum up a list of things? Look at each thing and add it together. That's it. So sure, straightforward, but don't think like, oh, well, okay, why would I do it? It exists. Like, right? Why would I make a loop to do it when I can just sum it? That sum function is going to have to loop over all elements in that list. Now, how many How do I have it worded here? Yeah. If I gave you a list of 10 things, how many times is this loop going to run? This is not a trick question. You should be able to answer this pretty easily. A list of size 10, how many times is that loop going to run? I need conviction.
10 times.
10. I love it. That's much better. Right? If the list was size 100, how many things are going to get added together? How many times is that loop going to run? If it's size n, where n is some arbitrarily large number, how many times is that loop going to run? If I doubled it to 2n, how many times is that loop going to run? Interesting. So, if I double the size of the input, I double the amount of work this code does. Do you see? Seems obvious, right? Okay, cool. But that's an interesting and important observation. If I make the input bigger, this function has to work harder. There are some times where maybe if I make the input bigger, the function doesn't have to work any harder. There might be, like for example, somebody, when doing, I think 2 weeks ago, maybe it was 3 weeks ago, the lab where we were doing the like return from vacation day thing, right? Somebody wrote a loop. Was it you? Yeah. It was you, right? Which entirely works, right? They wrote a loop to subtract 7 over and over and over and over and over until like it couldn't do it anymore, and then like that's how many days were left, right? Cool. And what's interesting about that code, now by the way, how this actually works if you really open up the computer and look at everything, this is another story. But I'm going to use this as an example. If I get like as the number of days increases, the number of times that loop is going to have to run is going to increase, right? Right? So like if n is like 100 and you subtract 7, you're going to subtract, that loop's going to run however many times. But if you make it 1,000, it's going to run more. If you make it 10,000, it's going to run more. But if you just did the modulo, there's no looping, right? It's not going to take longer with a bigger number, right? So your choice of code, how you code things, actually really matters. A couple weeks ago, I was talking about like what makes code good versus bad, right? And there's a lot of different metrics we could use to measure it, but one of the important metrics is what we call computational complexity. This is what we're talking about right now. Yours, and I'm picking on you because you did it, and I remember.
It's okay, I get it.
If I make n sufficiently large, and we did this, right? I said like type in like 10 billion, and you hit run, and it was like, it took a while. And then I think you were sitting right next to him, right? And you did it with mod, and you put in the same number, and it was done like that. And it would only get worse if we made n even bigger. Yours would still run like that. Yours would take even longer. That would be an example of like, okay, given these two ways of coding it, you should pick the mod one, not the loop one. But more on this concept a little later. Any questions about that though before we move on? Yeah.
When I put in that identical code that you did, it just counts to 9.
Well, it's probably not identical. So there's been a reoccurring theme this year. I wrote the same code as you, but it did something different. You didn't write the same code as me. Other questions? Did you find the difference? I'll leave it up for a sec. Pardon? Yeah, is your return indented? Yeah? Well, if it's counting to 10, you must have like a print in here.
Could be any brackets.
All right, well, something's different. Other questions? Okay. Now, we were talking about data structures. And a data structure is just that, right? It's some structure of data, a way we can like structure our data and it'll make our lives easier. Lists are an insanely powerful general purpose data structure. Probably like the most common that you're going to use, right? And we start with that, great. Lists are actually relatively complex data structures. There's a lot like going on with them, but whatever, it's a data structure and it's still not too crazy. There are a lot of other data structures out there. Tuples, dictionaries, and sets are some examples of those. This is not an exhaustive list. You can invent your own data structure however you want, but sets, tuples, dictionaries are also very popular data structures. For the purpose of this class, we're not using these things very often. Tuples is probably the most often, but they are still noteworthy to know about. Tuples. You may have seen this before, right? Where it looks like a list, but instead of square brackets, we use the round parentheses, right? I think in assignment 1, all of the latitude and longitudes were like in tuples, I think, right? We put them in tuples. Cool. Why not a list? Didn't really matter. Could have done it with a list. Now, there would be a good argument to use a tuple, but here we go. Let's just take this, and let's see, okay, so what makes them special? Right? It looks just like a list to me. I can index it. Right? Can I, some tuple at index 1 equals x. Tuples, based on what you just see right here, what can I conclude about tuples? They're immutable. I can't change them. And we like this. I know at this stage you always think, like I remember being where you were, and I think to myself, like, why would I want more restrictions? Lists are way more general purpose. I've got more freedom. Why would I not want more restrictions? Oh no, you want restrictions. It's much cleaner and safer, and the restriction gives you more control over how people use your code. Like if I had a data structure that you're going to use, and I want to make sure you don't mess with it, I'll give you a tuple, so it's immutable. You don't accidentally mix it up, right? Like that actually, it gives you, like these different options gives you more flexibility in what your code means. Okay, so it actually gives you like more semantic meaning. So that's kind of interesting. You also can't append to tuples, right? So they're really nice. They're also really handy when you just have like multiple pieces of information you want to like just package together real quick and dirty. That's what tuples are like. They're perfect for that. And in fact, an interesting thing is, and I always have a laugh, right? Because I'll argue with people. A, B. Oh, what? B, right? And if I go here and say return A plus 1 and B plus 1. By the way, traditionally speaking, and also same thing with Python, traditionally speaking, functions, just like in math, will only return one value. They can have multiple inputs, but they should only ever return one value. That's a thing. But in Python, you can return multiple values. And I'll show you how this works. X, Y equals some function, and then I've got like A, B. No, let's do like 5 and 6. Print x, y. Right? Cool. Right? Neat. See what I did? It returned 2 values. Right? And because it's returning 2 values, they got assigned to x and y based on their ordering in the return statement. However, turns out Python, this is just syntactic sugar. Because what's really happening is Python went and added this to your code whether you like it or not. It wrapped all that data into one tuple and it returned one tuple. And tuples are a beautiful way to have one thing store multiple pieces of information. Just like those x, y, or those latitude, longitude coordinates in assignment 1, right? Pair them together real quickly, a tuple's perfect for that. And I can even like really show you this. If I were to just do like x, and I print out x, we see the tuple. Type of x, it's a tuple. So turns out, no, you can't actually return multiple things in Python, but it does have some nice syntactic sugar to make it look like you can, but you can't. It really is just one thing. So that's an interesting little thing. When you do like this right here, you are unpacking the tuple like on the fly, where you know, okay, yeah. Where here, I'm not. But the number of elements would be important here, right? If you have like 2 and then, but there's 3, it's going to say, you know, not enough things to unpack. In fact, let's do that real quick. X, Y, Z. And what's the actual error? Not enough values to unpack. I expected 3, but I only got 2, right? So this is a way, anyways, to do that on the fly. Any questions about this? No? Now, dictionaries are deceptively, here, hold on, there was something here. Yeah. Dictionaries are a little deceptive. It's not immediately obvious how unbelievably powerful dictionaries are. They are insanely powerful. But it takes a little while to really get it. But because we are running a little low on time, I don't want to start dictionaries right now. Very quickly, a dictionary is kind of like a list, but instead of indexing with like 0, 1, 2, 3, 4, you can index it with whatever you want. Like strings, for example. Pretty neat. But anyways, a little while ago, so there are, look, if you did test 1, I'm not talking about lecture content anymore. If you did test 1 and you did really well and you're proud of yourself, good, 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 good. But I warned you, don't get comfortable because test 1 ultimately kind of easy. There's not much I can ask. The most complicated thing I could ask you was put some if statements inside a function, right? Since then, we've covered a lot more stuff, right? So, okay. Now, if you did test 1 and you were like, oh man, that was so hard, I don't know. Look, sometimes with programming, maybe like you get it to a point, but it just hasn't really like clicked yet for you. And often what you'll find with programmers is a lot of programmers will have a story of how and when things started to click for them. There tends to be like a moment. Some of you in here may have already had that moment. Some of you maybe will never have that moment. It always just kind of made sense, I don't know. And some of you will have that moment. It's going to happen. And I'll tell you exactly when and where I had my click moment. Back when I was doing this, we were having a midterm, and we had a written midterm, and we also had a practical midterm. And it was set up so there were like 6 questions. 3 were like that turtle graphics stuff where you would draw, and 3 were based on sound. Okay, and at that time, back when I was doing my undergrad, sound was our multimedia was a very popular way of like teaching programming. So drawing pictures with turtles was good. And you can kind of see why, right? You write some instructions and you can see visually what's happening. And then sound. The idea with sound was sound would be like a linear collection of like amplitudes that if you played, you could hear something. Effectively like a list, right? Turns out that we have since kind of like thrown that away because it ends up being like really confusing to people. But whatever, at the time, there it was. And the way the test worked was you would show up and you would roll a die, and based on what you would roll, you would have to answer one of the questions from the turtles, from the drawing, and one of the questions from the sound. And they even gave us all the questions beforehand. They gave us all 6 questions beforehand, said you could practice all you want. But the day of the test, you're going to have to do 2, and you're going to have to submit it. Great. So I did all the prep I could. The graph, the like plotting ones, the drawing ones with the turtles, easy peasy. I had those figured out. It wasn't too bad. But the sound ones, I couldn't wrap my head around. I couldn't figure it out. It didn't make any sense to me. And I tried everything I could. I sat banging my head against that keyboard for hours prepping for it, but it never clicked for me. And then the day of the test, I roll the die, I get my Turtle Graphics 1. It was easy peasy. I think I had to like, you have to write a function where it takes some n and then you have to draw a staircase with like n steps or something. I don't know, something like that, right? That one was easy, but the question I had for the sound one, it didn't matter which one I got. There were 3. It wouldn't have mattered which one I got. I didn't understand any of them. But the one I got was take a sound file of this guy that's saying rabbit. So it's just if you hit play, you hear rabbit. And half the frequency, okay? So what's expected, right? Well, if you half the frequency of like the sound of someone saying rabbit, you would hear like rabbit, right? So that's what's expected. So I'm there in the room writing the test. It was like 2 hours or something we had. In like 10 minutes, I had that one done, the drawing one. And then for the rest of the time, for the rest of like the hour and 50 minutes, I was just staring at the computer, trying everything I could to make that sound one work, and nothing would work. It wouldn't even run. Meanwhile, like no one had headphones. We were in a room like this, and everyone's little computers you can hear like, like people are solving it, and I didn't know what was going on, right? I'm freaking out. And at this time, I'm like, oh my gosh, I'm gonna have to drop out of university. I don't understand any of this. I'm so stupid, you know? Like it didn't make any sense. And then finally, and I was just throwing everything I could at the computer just to see what would stick. And then finally, I think there was like 10 minutes left. I hit run. And what did I hear? I heard, rabbit. I was wrong, but I immediately knew at that moment, everything made sense. The universe made perfect sense to me. I knew exactly what I did. What did I do is I doubled the frequency. I didn't half it, right? Oh, so instead of multiplying, I need to divide or something, right? Like, or vice versa. It's like I realized what I did wrong, but it was that moment was my click moment. There might be some people in here that already know that click moment for them. Like I said, some people never have one because maybe it always made sense to them, and some people might still be yet to have it. But you're never going to get that click moment if you're not doing it. You got to do it. If you sit down and work on assignment 2 for 3 hours and then give up and ask ChatGPT, you are not going to be successful. You are going to probably fail the course. That's not the way to do it. You have to slog through it to learn it. ChatGPT is a great tool for answering questions. It's a terrible tool for learning anything if you don't use it right. And judging from assignment 1, there's a lot of people in here that use ChatGPT. It's obvious. So, if that's you, and you get perfect on the tests, great, you figured it out. But if that's you, and you get 4% on the final exam and come to me saying, but I got perfect on all the assignments, I'm going to look you straight in the eye and say, I know exactly why. You got to slog through it to get it. That's the way it is. And it's not going to take you 2 hours to do an assignment. If it does, great. Expect it to take 8. If after 8 you've made no progress, come see me. Come to office hours. Woefully under attended, right? but you gotta slog through it. It's the only way to figure it out. All right? This is not condemnation. This is motivation, right? All right, I'll see you all later. Yeah, I hope so.